All right. Hello. So today we have a few things to talk about. A few of the big things. You do have your lab, which is due today. So try to work on that. Try to finish that. Try to get with the group. I'd rather you try to work with the group if at all possible. Um, so try to do that. Again, things coming up. You will have a test early next week. Your class is Tuesday, so it'll probably be on Tuesday. It might be put on Monday depending on what Lambert's doing, so we can have it on the same day. So just kind of be expecting that. You have your test review, which is up on Google Classroom. Not Google, it's on Google Classroom, but it's through the College Board website. So to go and you'll do that. So make sure everyone's doing that, trying to do that, and asking questions. Um, some other things, assignments. I've been trying to go through and grade those, and there's been a few things that have really complicated how long it takes to grade all of the assignments online for every single thing. So one thing I know a lot of people are struggling with Google Classroom. I'm pretty sure the problem is just that every single person is using Google Classroom. Like I think we only have so much space allotted as Garland ISD for all of the Google services and so much bandwidth and everything like that. So if you're trying to upload something and it doesn't upload initially, maybe try again, maybe wait a few minutes, try again, or try uploading things at off times, like either early in the morning or later in the afternoon. Might help with that. But yeah, if at all possible, try to upload your attachments through Google Classroom. It just makes it a lot easier for me to grade them. Um, I gave you the title I want. If at all, like if that completely fails and you try to turn something in Google Classroom like 10 different times and it keeps not working, then the next option would be email. So if you do email me an assignment after you tried a lot of times to get it on Google Classroom, I do want your name, I want your class period, and I want the assignment name. That will just make it easier to keep track of things. Otherwise, it gets really painful. Some people have been doing Google Drive, which is a little bit more time consuming because what ends up happening is it has to open up in Google Drive. Then I go through, then I close that out, then it's back in Classroom, which might not sound like a lot, but it about doubles the time that it takes to grade assignments. And if every assignment is doubled in time, then I'm going to spend twice as much time grading. So I could add like potentially over an hour each day. So try to get it everything attached on Google Classroom. It'll just make it a little bit easier, less to deal with on my end. Um, yeah, those are the big things. Oh yeah, and then late work. I'm not going to take any late work that's over a week old. So if it's due Wednesday, you have until the next Wednesday. Late work doesn't announce that it's late. It doesn't say, "Oh, you have this many late things." I have to actually manually look through the assignments. So any late work, just kind of be aware that I might miss it if you turn it in late. So try to get things turned in on time or really close to on time. That way it's a little bit easier to make sure you get a grade. Any questions on all of that before we start with this? Yeah, so that's the big thing. Just kind of a little bit easier on my end because yeah, there's a lot of assignments coming at me from all different directions. It's just really hard to keep track of. And so just really please try the Google Classroom first. So yeah, if you already turned in a paper copy of the spring's classwork or homework, then I don't need to see it. So if you have a grade in the grade book for those, it's fine that it says missing on Google Classroom. That's not going to affect your grade whatsoever. So yeah, so if you already turned in a paper assignment before the break, especially the spring classwork and homework, you don't need to do that. If you have any late work, again, with the format I said, the title of the email, you'll say your name, class period, and the assignment name, and you can email those to me as long as it's more recent late work. Um, But yeah, if you have any late work, get that in soon. Otherwise, I'm not going to grade it just because there's so many things I'm trying to grade. Any other questions about that? No other questions? Everyone's good on those? All right, so there's no other questions on that. Let's look at our warm up. So the upcoming test is going to be, again, simple harmonic motion, all about springs and pendulums. Last topic we do, and we're going to just have a lot of review after this. So that's a good thing. We're not having to learn a lot of new things from home. So we've already covered everything that's important. All right, so we have a mass M attached to a spring constant K, executes simple harmonic motion. So again, simple, small deviations, so very small distances it's moving up and down. Harmonic motion, that means it's going back and forth through an equilibrium position. So it's going back and forth about an equilibrium position. If I go up, it's getting pulled down towards equilibrium, but the mass goes down. The mass is getting pulled up towards equilibrium. That makes it harmonic. And then without damping. So damping is talking about losing energy. So this would be like in air or in water, there's a friction that as this thing moves, it's going to slowly stop. Or even just the spring itself. When you bend metal continuously, it warms up, and that's going to be losing energy. So we're assuming that it just keeps going back and forth without any sort of energy loss. All right, so on our axes provided below, we want to sketch position time, velocity time, and acceleration time graph at the, given that at the time t equals 0, the mass is pulled down to position of x naught equals 1 relative to the equilibrium. It's released from rest. The period is 2 seconds, and we're going to use the tick marks on the t-axis as seconds. Your graph should have the correct sign, phase, period, and you should label the peak positive values in terms of the givens on the coordinate axis. All right, so there's kind of a lot going on here. So first of all, for your warm-ups, I do want you to write your warm-up questions and take a picture of that, just like we normally do our warm-ups. You don't necessarily have to write the entire question exactly, but at least summarize what the question is asking and give the key points. We're going to work through some classwork. You don't have to write all the classwork questions though. So warm-ups, I still want you to write the question or at a minimum summarize it. The classwork, I'm not going to make you do all that. So let's try to sketch out some graphs here. So we have our position with respect to time, then we have our time axis, and then it says that we're using each of the tick mark as seconds. 1, 2, 3, 4. Yeah, they have 5 on there. So this would be 1 second, 2 seconds, 3 seconds, 4 seconds, 5 seconds. All right, so we have position on here. We pull it to position 1. So what 2 points does it go between? What 2 positions are going between?
1.
And -1. And we're going through our equilibrium position at 0 right here. All right, we pull it. Where does it say it? The mass is pulled to. I just saw those words. Why are the words? Yeah, never mind. Maybe I just read that wrong. So it's pulled to position x equals 1 relative to the equilibrium and released from rest. Yeah, I'm going to change it. It says pulled to. That's kind of weird to say it's pulled up to, because I would say that's pushed. I'm going to say it's pulled down to -1. More so because the wording is just really weird to say pulled up to position 1. Uh, no, I think that would be more explicit. Do you want me to start it at +1? We can just say it's pulled. We can just say it's pulled up to. I'll just call that +1 if you already did that. It's just really weird English. I think they would. I think they would use a little bit better wording on the AP test. Yeah, if you can't hear me, I guess try turning up the volume or leaving and then reopening. All right, so we'll say it starts at +1. So we pull it up and release, and it's not at equilibrium initially. We release it from a position away from equilibrium. Now, what's our period equal to? So our period is equal to 2 seconds. So that means I know my position at this point. So it's probably one of these. It's either going to be at 1, 0, or -1. All right, so our period is the amount of time to complete one cycle. So if it completes one cycle, we've returned back to our initial position. So at 2 seconds, I've completed one full cycle. So where am I going to be exactly halfway between these? At 1 second. So at 1 second, we're going to be at -1. Do that right there. Which means, so 0 seconds, I'm at 1. 1 second, I'm at -1. 2 seconds, I'm at 1. 3 seconds, this is cyclical motion repeating itself. So that's -1. 4 seconds back to +1. 5 seconds back to -1. You actually can use derivatives, but you don't have to. So yeah, if you're in calculus and you know how to do derivatives, that is actually really, really helpful for this. All right, so how do I connect these dots? Just like a sawtooth wave that's just like jagged up and down. All right, so sine wave, in particular, this one's not, I mean, it's the sinusoidal, but what type of wave is this one? So this is going to be a cosine wave. Not that you really need to know that. But yeah, we have a sinusoidal type shape. So we have a repeating motion. So this is what our graph is going to look like for any sort of simple harmonic motion. We're going to see some sort of sine wave type graph. So this would be the same for, say, a pendulum. Looking at the pendulum moving back and forth, it's going to follow this same sine wave motion with respect to time. All right, so yeah, so we have this sine wave here. So now let's kind of, before we really get into our velocity time graph, let's kind of talk about what's happening at each of these points here. So let's talk about, say, at 0 seconds, half a second, 1 second, 1.5, and 2 seconds to kind of describe what's happening here before we fully draw out our velocity time graph. So kind of think about what's happening to our velocity at each of those points while I'm drawing this out. So at 0 seconds, what's happening to my velocity right here? Yeah, why is my velocity 0 right there? So starts from rest, that's one thing. We can say starts from rest. We can also look at our energy. So we're at our maximum displacement, which means our kinetic energy is 0, and therefore it's all in spring potential energy. You can look at gravitational potential energy. Again, whenever we have a mass on a hanging spring, we're just going to, a lot of times, just kind of imagine the new equilibrium is where the mass comes to rest and not worry so much about gravitational potential energy. So yeah, so no kinetic energy. All my energy is converted to potential energy. All right, so I know my speed is 0 right here. All right, so let's look at half a second. What's happening at half a second? Am I moving in the positive or negative direction? All right, so we're moving in the negative direction. I'm going from 1 to -1. So I have a negative velocity. So that means probably somewhere down here. And what specifically can I say about my speed here? Big or small? That's my biggest speed. That's my maximum speed. So I have the maximum speed. And what do I call that point? So that's my maximum speed at the equilibrium position. So at equilibrium position, I have my spring potential energy is 0 joules, which means it's all the energy is in kinetic energy. All right, so all of my energy is in kinetic energy. I have the maximum speed. I'm moving backwards, so I'm going to have the maximum negative value right here. Now, we can't really solve for this value here without using calculus, so we're not going to mess with that. All right, so right here. Then we get to 1 second. All right, what's happening at 1 second? Zoom, zoom. No, not at 1 second. Yeah, right at 1 second, our speed is back to 0 meters per second for the exact same reason at 0 seconds, right? So again, we're back to that maximum displacement. So maximum displacement, so I have 0 joules of kinetic energy, and all energy is in spring potential energy. And then, yeah, we can also just think of it stopping. It stops going back so it can start going forwards. So in order to change direction, I have to stop before changing direction. So at 1 second, we went to stopped. Should have given myself a little more space. That's all right. 1.5 seconds. So what's happening at 1.5 seconds? All right, so we're moving in the positive direction, -1 to +1. So I have a positive velocity. Big or small positive? There we go, maximum positive velocity. So I have the maximum speed there because we're at equilibrium. So again, I have no spring potential energy. Therefore, all of my energy has gone to kinetic energy. And again, another thing that might be good to talk about when we're talking about these is that it's the total mechanical energy is constant because they said no damping. So yeah, so equilibrium, no spring potential energy, all that energy has gone to kinetic energy. I'm moving forward now, so I have the maximum positive speed right here. And then I don't really have to talk about 2 seconds because what is 2 seconds identical to? Yeah, it's the same as 0 seconds. So 2 seconds is going to be the same at 0 seconds, where I'm again at that maximum positive displacement. So I have no kinetic energy, all spring potential energy, I go to 0. Same story with 2.5 seconds is just like half a second. Those are the exact same. And then 1 second is the same as 3 seconds. And then everything is repeating. 3.5 is the same as 1.5. Not necessarily. So you're probably not going to have to write all of these. This would be something I would ask individually. So I could say, instead of asking all this, I could say, what time does the, after time t equals 0, does the mass achieve the maximum positive velocity? And then, so if we said, oh, so at 1.5 seconds, we achieve the maximum positive velocity, then we would explain why. We would say, well, we're at our equilibrium position. So because we're at equilibrium position, we have the maximum speed. And then because I have this is the first time I have a positive slope on my position time graph, then I have a positive velocity. We can use slopes. If you notice my wording, I was talking about slope. When I say we go from positive position to negative position, that is like with respect to time, we are talking about slope when I say it that way. So yeah, you could say I have a negative slope on my position time graph at 0.5 second, so I have a negative velocity, or I have a positive slope on my position time graph at 1.5 seconds, which means positive velocity. So yeah, that is a perfectly valid way of going about this. I'm just trying to relate this to our simple harmonic motion we've been working on. So I'm trying to relate it to our concepts that we're using now. So we can kind of extend this out. So our graph is going to repeat itself. So then like this. All right, now is this one going to be a sinusoidal wave or just jagged? So sine, and particularly, that's not a, sine is close, but not exact. Not a positive sine, but a negative sine. So yeah, we have cosine x, negative sine x. And this is where, if you're in calculus, you know the derivative of cosine is negative sine. And then you should be able to jump the gun and get the next one pretty easily. You could actually try including all the pi's and everything in there. It doesn't matter so much, though. All right, questions about going from position time to velocity time before we go to acceleration time? Yeah, we can't really solve for that in algebra-based physics because that would involve calculus. Yeah, we also, yeah, there's a few things we would need to know to actually get that. So we're not going to actually be able to solve for that maximum velocity. We could call this like positive Vmax, negative Vmax, and we're definitely not going to be solving for acceleration here. Do we have enough information to solve for that? Actually, we might have enough information to solve for that. Yeah, I guess we could solve for that. Yeah, let's actually solve for that. So how would we solve for that? All right, so we can use spring force. So we pull this down. It says 1. I assume that means 1 meter. We're not given a spring constant, though. Yeah, no, yeah, that's a mess. We're not going to do that because we don't have a spring constant. That's a numerical. Yeah, Vmax can be solved from energy, but we don't know spring constant. So yeah, we could go through and say 1/2 spring constant times that 1 meter squared is equal to the 1/2. It's the mass, just says mass m, right? Mass times v final squared. So we could do this, 1/2 divides out, and we could just do the final speed is going to be the square root of spring constant divided by mass. Yeah, don't use kinematics for this. But yeah, we could do that. We could do this one is at positive square root of spring constant over mass, and this one would be at negative square root of spring constant over mass. Yeah, I guess we could actually solve for what the spring. Well, but we don't know the mass though. So yeah, not knowing mass or spring, yeah, it's not going to make it look much nicer. Um, I'm less concerned about that right now than the actual concepts. Trust me, we'll go through plenty of math with spring constants. Um, yeah, but what's your mass? You don't know mass or spring constant. Or you're saying you solved for, oh, you actually substituted in. Yeah, I guess you could do that. Yeah, you can do that. Pi squared. So yeah, right around 10. If you really want to, you can use 10. Again, I'm not super concerned about that at the moment. All right, so the last thing to look at is acceleration time. And then, yeah, since you actually solved for your spring constant and all that, then you could solve for it. Again, I have other things I'm worried about right now. So I'm just going to call this positive maximum acceleration and negative maximum acceleration. And for your calculus people, we went from cosine to negative sine. What is this shape going to be? Close, negative cosine x, yeah. So if you're in calculus, this should be straightforward. Otherwise, let's actually go through and look at this. And I'm going to pretend that we don't know our velocity time graph because we could have horribly screwed that up. So yeah, so we're going to use net force. So let's be looking at our net force. So at time t equals 0, what's my net force right here? Oh, this is the spring energy turning into kinetic energy, but yeah, I didn't actually end up using that. All right, so that's where I have my largest spring force. So I have the maximum positive displacement. So I do know I have a maximum spring force. But which way is this acting, up or down? Yeah, this is going to be that maximum negative spring force. So this is where on our formula chart, we have that spring force is equal to spring constant times the magnitude of displacement. Some of you were saying in your book, you were wondering why they use spring force as negative spring constant times displacement. And again, that's all just, we normally do this because we don't care so much about direction. We're handling direction elsewhere by putting in positives and negatives elsewhere. But for this one, it is kind of good to look at the negative spring constant times displacement. We look at when we're at our highest position, we're getting pulled down, and we're at our lowest position, we're getting pulled up. So at time t equals 0, we're starting at our highest position, and we're pulling down, getting accelerated downward. So we have our maximum negative spring force. And again, we know acceleration is equal to net force divided by mass. So my net force is down, therefore I have the maximum negative acceleration. So maximum negative acceleration. That's looking good. Negative cosine starts there. Then we look at half a second here. what's my acceleration right here? Nothing. Why do I have no acceleration there? So our displacement from equilibrium is 0. We're at equilibrium. So we're at equilibrium. So because we're at equilibrium, that means our spring force is 0 newtons, and therefore our acceleration is 0. So we have no acceleration right here. Wait, what did I? That's half a second, not 1 second. Sorry, I drew that in the wrong spot. Half a second, I have no acceleration. Then at 1 second, 1 second, I'm all the way down here. So what could I say about my spring force at 1 second? All right, so I have the maximum acceleration. That's not. Sorry, I'm trying to adjust my lighting without washing out the entire paper. All right, so we're maximum negative displacement. So I have the maximum spring force again here. Again, spring force, spring constant times displacement from equilibrium. And which way are we getting pulled here? I'm at my lowest point. Am I getting pulled up or down? So we're getting pulled up. So I have the maximum positive spring force. Therefore, I have the maximum positive acceleration. And again, this would be like something I would just ask you, what time do I have after time t equals 0? Will I experience the maximum positive acceleration? Well, that would be looking, well, I need to look at one of my extreme points. I'm going to have a maximum spring force. Well, if I'm at the maximum point, I'm accelerating down. If I'm at the minimum point, I'm accelerating up. And we could talk about 1 second being our answer. Then 1.5 seconds, back to equilibrium. So because I'm at my equilibrium position, that means I have no spring force and no acceleration. So back to 0 here. And then we see 2 seconds again is identical to 1 second. So back here, and then my graph repeats itself. Just like the other ones, I'm going to get a sinusoidal wave. Something like that. And then that matched my prediction for those of you in calculus, cosine, negative cosine. Or I could look at it this way. Concave up on position time means what to our acceleration? Or concave down on position time, I mean. So concave down on position time means negative acceleration below the x-axis. Concave up on position time, positive acceleration above the x-axis. Concave down, negative acceleration. Concave up, positive acceleration. Concave down, negative acceleration. Concave up, positive acceleration. It's another way you can look at that. Questions on that? So that's a whole lot of information. Again, there probably will be a question like this on your test where you have a graph that you're analyzing. Again, I'm probably not going to make you analyze every single individual point, but I could ask you about specific points. I could make you draw this graph and then ask, where do I have the first time where I have the maximum positive acceleration? Or at what point do I first stop after time t equals 0? Or what's the first time where I reach a maximum negative velocity, or the first time I reach a maximum positive velocity? So you're probably not going to have to write every single individual one of these, but there's a good chance you're going to have to write some of those. It says label the peak positive value in terms of the given coordinate axis. I mean, I guess you can go through and actually solve those. I don't really care about that. Yeah, you can just put positive, negative acceleration max. Yeah, I really don't care that much about that. I care more. The reason I gave this warm up was more so talking about how to draw these graphs, seeing that they're all sine graphs or cosine, sinusoidal, so some sort of sine or cosine, and then being able to figure out what our velocities and acceleration and forces are for all of these. Any other questions on your warm up? So for your warm up, make sure you write the question out, take a picture, post that on Google Classroom. And then I also posted classwork that we're going to work on, so you can also take a picture of that and post it. So if you do all of these, you'll get a free 100 for a classwork grade. And if you're confused, you do not need to print out the classwork. If you want to print it out, you can, if that's helpful to you. You don't have to write the questions for the classwork. Just at least write the number and write the answers, and we'll do as much as I get through. What was I going to say? I lost track. Oh, you might be confused yeah, you turn it in under the 325 class. So you'll take a picture of both the warm-up and the classwork we do under the class assignment you did to get here. Yeah, what is it called? Under the one that says 325 class at 10 a.m. Yeah, you're only turning in what we do here, nothing more. So if we get through all of it, then yeah, you can turn it in all. But if we don't quite get through all of it, then yeah, you don't have to. I mean, you might want to do it just for practice. And then the grades I've kind of shifted because I'm lazy to making your grades out of 9 points because it's easier to type a 9 than a 10. So yeah. All right, let's start with 1. Now, again, the AP test isn't going to give you any free response question, is what it's sounding like, but they still have some really good concepts in them. So I could easily see a question like this appearing not as a multiple choice, but as a free response type thing. So this one is talking about we have 2 simple pendulums. Pendulum A has a length A, pendulum and mass A. B has length B and mass B. They both have the same period. The only thing that's different between their motions is the amplitude of A's motion is twice that of B's motion. Which of the following is true? How should we probably start with this one? Probably start with the period equation. That's a good place to start. So period, and we're talking about a pendulum, so period of a pendulum is 2 pi square root of length of the pendulum divided by acceleration due to gravity. All right, the only thing that's different between their motions, the amplitude of A's motion is twice that of B's motion. So if those are the only things that are different about the motion, what's the same for their motions? Period. And it doesn't explicitly state this, but I'm pretty sure they're also both on the same planet. Unless they explicitly tell you you're on a different planet, you're on the same planet. So, same period, same planet. So what can't be different? What has to be the same? Oh yeah, classwork. You do not need to rewrite the question. Yeah. I still want you to rewrite the question for the warm up though. But yeah, and if you want to print out the classwork, you could, but you don't have to. So yeah, because they have the same period, same acceleration, 2 pi is the same. That means they have to have the same length. Same length. Now, a few of these are talking about masses. Does mass affect the period of the pendulum? No. Yeah, you can just print the packet and do it there. If you have a printer that's readily accessible, you can do that. You're just going to get a free 100 for this. So more so, I'm just making you write the answers to the classwork to show that you actually did it. But yeah, it should be a nice, easy free 100 and a little bit of study for the test. But yeah, there's no mass in here, so mass doesn't affect anything. So it's probably not going to be A or B talking about mass A equals mass B for either of those. So that leaves C or D. So whatever the ratio of the masses, that sounds more right. So what is it, C or D? C. So we don't care what the masses are, but they do have to have the same length string. All right, so again, no multiple choice on the AP test. We'll get more information on that April 3rd. It doesn't sound like they're going to do any multiple choice, but multiple choice questions are still good to practice because I could easily turn that into a free response type question where you're answering what has to be true about the masses. And you say, well, it doesn't matter what the masses are. What has to be true about the lengths? Well, they have to have equal lengths because, and then showing the equation and all of that. All right, 2. So the AP test, no, the AP test is not April 3rd. April 3rd is just the date that they said they're going to release more information about the AP test. I don't know when they're going to do it. Yeah, it sounds like it's only going to be 45 minutes of free response. But yeah, they'll put out more information. I would just assume it's still going to be on May 7th and then wait. And if anything, it might be delayed. So May 7th or later is probably what you should have in your mind. All right. Is the test you're giving us? Oh, yeah. Never mind. Sorry, I didn't read that right. Yeah, the test I'm giving you is only going to be free response. So, again, I did give you multiple choice review. It doesn't mean those aren't important. Those still have extremely important concepts. It just means you have to make sure you're getting the concept as opposed to figuring out how to guess a multiple choice answer. So, yeah, your test is only going to be free response. Why did it have to be free response? Because multiple choice is too easy to cheat on. And free response, they can do plagiarism detection, yeah, pretty much to prevent cheating. And again, I'm going to keep saying this over and over again. Please don't try to cheat by looking at a website when you do it, because then you're going to copy and get flagged for plagiarism. And if you sign an agreement saying that you won't cheat and then you cheat on this, there's a possibility they could go through and invalidate every single one of your AP scores and your SAT scores. Now, not saying that's what they will do, but they could do that. So I wouldn't play with fire. Yeah. Well, you're getting into legal questions. I think they kind of have the thing where like you are not an adult, so you can't technically sign a legal document. So you might be able to fight them on that. But College Board brings in what, like $2 billion a year. You're not going to be able to fight them. They're going to be able to afford better lawyers than you. So you're pretty much stuck doing what they want, regardless of what the law says. Yeah. Did College Board set a plagiarism detector in Google? The plagiarism detector looks everywhere. So it looks through Google, it looks through as many different sources, it compares different people. You have great lawyers. It actually doesn't matter. Even if you have like a really good lawyer, they have dozens. And one of the techniques they can always do is they can always just sue you for a lot of random things until you drop your claim. I mean, just welcome to how law works. just use Netscape. Jeez. Doesn't Netscape still put out new browsers? Oh, it's completely dead. I mean, I would hope it's dead. All right, let's do 2. So 2, a small dart of mass 0.02 kilograms launched at an angle of 30 degrees above the horizontal with an initial speed of 10 meters per second. At the moment it reaches the highest point in its path and moving horizontally, it collides with and sticks to a wooden block of mass 0.1 kilograms that is suspended from the end of a massless string. The center of mass is 1.2 meters below the pivot point of the string. The block and dart swing up until the string makes an angle of theta with the vertical as shown and air resistance is negligible. All right, I really like this question because what concepts does it deal with? I mean, I don't know what they're going to do with false positives. But yeah, it deals with projectile motion. So we have a launch at an angle, so we're going to have to deal with that. What else does it deal with? Momentum, collision. We have a collision. The dart goes, collides, and sticks with the mass. And then it swings up. And then so we also have some pendulum motion and energy. So yeah, this is one of those questions I could easily see on the AP test where they have multiple concepts and SMH, definitely SMH. So let's go through and do this. So A wants to know the speed of the dart just before it strikes the block. So that's looking while we're in projectile motion. And sorry, Samir, but we're still not doing kinematics for this one. Even though it's a kinematics type thing, we don't need kinematics. All right, what point is the object is the dart in its motion when it collides? So we're at our maximum height. So we're right here. What direction are we going at the highest point in the motion? So we're going to the right. All right, so what do we know about our components of velocity? So it's all to the right. So at the top, my y speed is 0 meters per second, but my x speed, what can I say about the speed in the x direction during the entirety of the motion? So the horizontal component is constant. So that means right here, I just need to split this up and figure out what my x component of velocity is. So this is my initial velocity. But once I get my x component of velocity, it's going to be equal to my velocity at the highest point. So launched at 10 meters per second. I'm trying to figure out how much of this goes in the x direction. I could figure out that y direction, but that ends up not being important. All right, we're launched at an angle of 30 degrees. So I know 10 meters per second. I'm trying to find my x, my angle here. So opposite or adjacent, sine or cosine. So cosine, because we're dealing with our adjacent. So cosine theta is equal to the adjacent over hypotenuse. Ka. All right, so cosine of 30 degrees is equal to my adjacent is what I'm looking for. My hypotenuse is the 10 meters per second, so we'll multiply this over 10 meters per second times cosine 30. And again, 30 degrees, so make sure your calculator's in degree mode. If we do end up staying on lockdown this long and you do end up taking the AP test from home, then you're probably going to want to make sure you have some sort of working calculator. Yeah, so there's a few ways. I'm just going to leave this at 8.66 meters per second. If you look on the back of your formula chart, again, everyone should have one of those. It does give us what cosine of 30 is. So 10 times the square root of 3 over 2. So you could just have 5 square roots of 3. Can we use Desmos? I do not know. This is something that I'm sure they're going to address on April 3rd. I have no idea what approved calculators they have or how they could even say that. I mean, TI has a free. Yeah, I think they're going to try to make you use a lockdown browser, but I don't know how they could do that because, I mean, I have like 3 computers in this room with me, so I could just easily use a different one. Yeah, I have no idea. I'll see. They'll probably address this on April 3rd. All right, so my x velocity is 8.66 meters per second, and my x velocity is constant. My y velocity goes to 0. So my velocity at the time of the collision is just 8.66 meters per second. Everyone okay with that? Never done with projectile motion. Oh, I kind of jumped the gun too soon. We do get to use a little bit of kinematics, really simple kinematics. B, calculate the horizontal distance d between the launching point of the dart and a point on the floor directly below the block. All right, so we're talking about horizontal or x distance. I guess I should probably call that d. It doesn't really matter. Displacement and distance will be the same here because it's only going forward. So, accelerating or not accelerating in the horizontal direction? So no acceleration and no horizontal acceleration. Again, I know you're just typing it real fast there, but just when you write this out, make sure you don't say no acceleration, no horizontal acceleration. They can't stop me because I can't start because I don't have Wi-Fi. Yeah, they're trying to get with people with Wi-Fi. Where are you using the Wi-Fi at? So no acceleration. So velocity is displacement over time. So speed times time is equal, velocity times time is displacement. We're moving at 8.66 meters per second for, well, we don't know time. So how do we get time? All right, so we can look at our vertical component. So we're looking at our motion from this point to this point. So we'll call the launch point the initial, and this point our final. All right, so our horizontal component was the 10 meters per second times cosine. My y is opposite, so what am I using here? Well, we will use the first equation, but I need to find my initial y velocity first. So y is my opposite side. So opposite is going to be sine. So 10 sine 30 degrees. And then what's my y component velocity here? 0. So I stop at the highest point. Stop moving up or down at the highest point. Sorry. We are still moving at the highest point. I'm just not moving up or down at the highest point. So my initial y velocity is pretty straightforward. Sine 30 is 1/2, so 5 meters per second. So I start with a y velocity of 5 meters per second. I end up at the highest point with 0 meters per second. We can use our first kinematic equation to do this. So my final y velocity equals my initial y velocity plus y acceleration times time. So my final y velocity is 0. My initial y velocity is 10 meters per second. we're accelerating downward due to gravity. I'll put it plus, minus 9 meters per second squared here. 9.8 meters per second squared times time. So how much time do we spend? Ten divided by 9.8 should be slightly bigger than 1. Wait, what? Because I can't read. 5 meters per second. Yeah, I literally just wrote that right here. 5 meters per second. So 0.51 seconds. So now I can put that in here, 0.51 seconds. And yeah, I'm going to round that just a little bit. So yeah, we do go about 4.42 meters in the x direction. Questions on that one? So we finally got to do some more kinematics. All right, no questions. All right, so C wants us to calculate the speed of the block just after the dart strikes. So again, the mass is going up here, and it goes and it collides with the pendulum right here. I use all kinematics. No, you're going to lose points. In fact, if you use all kinematics, I'll start taking points away from other places. Yeah, if your phone can't do that, then just wait for it to get uploaded. It'll be up about an hour after this stops. Yeah, which equation is that? Yeah, it was like it kind of looked like the time dependent Schrodinger equation, but there were a few weird things in there. All right, so that's what it is. So yeah, so what am I going to do to find the speed just after the dart strikes? Momentum. All right, so we have a collision, so momentum, and they stick together. So elastic or inelastic collision. So we have an inelastic collision. Let's look at our two masses. So mass 1, initial velocity of mass 1 plus mass 2, initial velocity of mass 2 is all equal to mass 1. Final velocity of mass 1 plus mass 2, final velocity of mass 2. All right, so let's call mass 2 the pendulum. And so the pendulum starts at rest. The toy dart has a mass of 0.02 kilograms, and it's moving at 8.66 meters per second, plus 0. Then the two masses go collide and stick together, so they have the same final speed. So I can just do mass 1 plus mass 2 times that final speed. So the dart, again, has a mass of 0.02 kilograms. The block has a mass of 0.1 kilograms. And we don't know the final speed. And yeah, you should get 1.44 meters per second. Anyone not get that? Or anyone confused? All right, D is where things get fun. So D wants us to calculate the angle theta through which the dart and block on the string will rise before coming momentarily to rest. So yeah, what are we probably using here? So the blocks collide, they swing up together, they go, they stop. All right, so energy. So we're starting out with kinetic energy at the bottom, and that's turning into gravitational potential energy. So this is right after the collision. And this is at the maximum height. So 1/2 mass. So this is after they collide. So mass of the block, mass of the pendulum, or mass of both. So that's mass of both. So we'll call that mass total times that speed squared. So we just got that 1.44 squared from the last part. All equal to, and then both masses swing up. So mass total times acceleration due to gravity, 9.8 meters per second squared. See, mass divides out, and we're trying to find the final height. By the way, make sure you're working these out and checking me, because I'm just doing this right now. I don't have my key on me. But when you do it, you should get something like 0.106 meters. But is that our final answer? No, yeah. They want us to get the angle through which the dart and block on the string will rise before coming to rest. So that's my height, not the angle. So let's try to draw this out big enough for you to see. So we have the pendulum here, and then it swings up over here to some angle theta. But we were only able to solve for this height here. I know this height is 0.106 meters. I know the total length of the string. What was the length of the string? They said that on the last page. 1.2 meters. Yeah, the center of mass is 1.2 meters below the pivot of the string. So we know this length of the string is 1.2 meters. All right, so what can we get here? First of all, what type of triangle do I probably want to make? Probably want to make a right triangle, unless all of you want to try using law of cosines, which I guess we could, but I'd rather just force this to be a right triangle. Yeah, I actually don't know why they chose the word right. I don't think it's from the root word correct, though. And I don't think it's from the direction either. All right, so we have this. So that means we're going to have to get this length here. I know this length, the hypotenuse length, is going to be the length of the string is 1.2 meters. So how long is my adjacent side right here? Well, this whole length is 1.2 meters. This length here is 0.106 meters, so I can subtract that out. So I'm going to redraw this triangle down here. If I stop breaking my lead, angle theta. So this whole adjacent side right here ends up being the subtraction of those two is 1.094 meters. My hypotenuse is the length of the string, which is that 1.2 meters. All right, so I have adjacent, I have hypotenuse. Sine or cosine? Cost. So we're going to use cost. Cosine of the angle is adjacent divided by hypotenuse. Cost co. So cosine theta adjacent is that 1.094 divided by hypotenuse 1.2. And then to undo the angle, undo the cosine, I mean, we need to do a inverse cosine of 1.094 divided by 1.2. Should get like 24.3 degrees. no gatherings. I think it's like 10 or more people. I know like a lot of grocery stores are starting to like limit the people who can go in at once, and there's like long lines outside. Right, did everyone get 24.3 degrees? All right, so 24.3 degrees. So when we look at this, is this actually simple harmonic motion? What angle have I kind of mentioned a lot of times for simple harmonic motion? Yeah, 10-degree angle. So simple harmonic motion, the angle is going to be less than or equal to 10 degrees. So this is outside of that range. So when we look at this, our pendulum equation is going to fall apart a little bit, actually. It's not going to be a terrible approximation, but it's not going to be the best. That said, I'm going to assume simple harmonic motion for this question. So in reality, it's not quite simple harmonic motion, but we're going to make the assumption here. So if you go further into physics, I don't think they even do this in physics C where they do the actual full thing. If you want to do this actual thing, then go to like a sophomore level mechanics class in college. So we're going to say it's simple harmonic motion, even though it's not here, because the AP test isn't going to talk about anything other than simple harmonic motion. So if that didn't make a whole lot of sense to you, don't worry about that so much. Yeah, the differential equation does not have a nice solution. It's not the worst looking thing in the world, but it's not great. So so the block continues to swing as a simple pendulum. Calculate the time between the dart colliding with the block and when the block first returns to its original position. So what are we going to use for that? So that's half of our period, right? So if it goes from here and it goes up and then back down, that's half of a period, right? For a full period, I would have to go up, back, and then return to my original spot. So there, and back for a full period. So we've only done half a period. Again, even though it's not simple harmonic motion, we will assume it's simple harmonic motion. We will assume our pendulum equation works. It's not the worst approximation we've actually done this year, assuming that this pendulum equation still works, but it's not the best by any means. So just kind of know that and accept it and go with it. So that's our period, but I only want half of a period. So 1/2 of the period of the pendulum is 1/2 times 2 pi times the square root. The string is 1.2 meters long on Earth. Top 10 worst assumptions tier list. A pretty bad assumption would be like you pull this to 90 degrees and let it go in that simple harmonic motion. That would be an absolutely terrible approximation. Throwing a baseball through water in a pool and assuming no water resistance, that would be a pretty bad approximation. Pi equals 3 is actually not a terrible approximation. Sine equals x is the approximation we're actually making here. So the whole sine equals x, that's the whole reason we're assuming less than 10 degrees, because less than 10 degrees, sine x is about equal to x. That is actually the assumption we're making for this equation. Pi equals 4, that would be a garbage approximation. Not so bad approximation. Pi squared equals g equals 10. Gravitational constant is 0. Yeah, the universe would not exist in any manner that we know of. Pi squared equals 16. I'm trying to think. Oh, I know the worst approximation I've made this year for any of the classes. It was inelastic collision assuming no energy lost. That was a really bad approximation. That was off by like a factor of 1,000,000. Yeah, no resisting force when water a ball is thrown through water. That's. I was trying to think of like what some of the worst things I could think of approximating. That would be pretty horrible. It's not quite as bad as like a ping pong ball thrown through water without any buoyancy or water resistance. Kinetic energy split between two objects in the springs. It depends on the spring. If the spring is massless, it's actually a good approximation. But if there's like a plate where the thing collides and sticks with it, then it's a terrible approximation. So if the spring has a really small mass compared to the object, it's actually not a bad approximation. All right, in the second experiment, a dart with more mass is launched at the same speed and angle. The dart collides with and sticks to the same wooden block. Is the pendulum going to swing more, less than, or the same as before? So launch a bigger mass with the same speed and angle. It's not going to stay the same. What is, if this has more mass, what else does it have more of? So same speed, so it'll be same initial speed before the collision. Because none of our kinematics is changing anywhere, right? So yeah, it has more inertia. My kinematics is all going to be the same. It's still going to hit going at 8.66 meters per second. So if this has more inertia, you're saying it has more mass. So it has more mass with the same speed, so it has more momentum. So if this thing has more momentum before the collision, what do you think this thing is going to do? So more momentum. That means we're going to have more speed after the collision. And that means we're going to have more kinetic energy after the collision. And that means we're going to have more gravitational potential energy at the maximum height. Or kinetic energy at the lowest point. So more potential energy means it's going to swing higher. So it swings to a greater angle. Now, wouldn't the mass almost cancel out as the higher momentum is reduced from more mass from the dart and the final momentum? No. The reason that won't cancel out is because where are we at? We're adding the two masses. So when we're dividing by the addition of two masses, we're going to see it's not going to cancel out. You could graph it with different values. Just instead of putting in the 0.02, just put x here. So you would have 8.66x divided by x plus 0.1. And you'll see your graph is going to go like this. Mass to infinity. Then you have a black hole. All right, is everyone okay with that? So you don't necessarily have to go through every one of these. I'm just extremely thorough, but more speed, same mass. No, same speed, more mass, sorry. So we have more momentum before the collision. So momentum is conserved during the collision, so this has to go faster after the collision because I have more momentum without changing the mass. So I have more speed after the collision, which means the block is going to end up with more kinetic energy than before. So if the block ended up with more kinetic energy, there's more gravitational potential energy being gained, which means this is going to swing to a greater angle. Now, F2, this is the one where we're just going to assume that it's still simple harmonic motion. More mass, we're trying to figure out the period of oscillation. So period of the pendulum is 2 pi square root of length divided by acceleration of gravity. Did we change any of these? We didn't change 2 pi. We didn't change the length. We didn't change acceleration due to gravity. So did our period change? No. So period is unchanged because we have the same length of string and same acceleration due to gravity. Now this is one where, again, if you do go further in engineering or physics, because our angle is outside of the simple harmonic motion range, we will see if this angle gets bigger, it will actually cause a small increase in your period. So in the real world, this will have a change for larger angles than 10 degrees, but we're just not covering that in this class. So we're going to say for this class, whatever angle we have, it's going to be the same period, and it will still be relatively close. So just kind of a disclaimer for anyone who goes on to a further class, so you're not going to be like, Mr. Beverly told me this wrong thing. All right, questions on those? No, we've done this for about an hour and a half, so I would say if you just turn in what you have on Google Classroom, so the warm-up and 1 and 2 on here, I'll give you a free 100 for the day. So if you have other things you have to go to and you're feeling really good about this, you can head off, and I'm not going to take 3 for a grade. But for those of you who want more practice before the test, I'll do 3 for you right now, all right? Does that sound fair? So if you feel good about all of this and you're not stressed about it, you can just turn in what you have for a grade. If you want a little bit extra, I'll go through 3 with you. So I guess if you don't mind typing yes, if you're one of the people who wants to go through 3, so I actually know some people do. Okay. At least one person. That's good. Enough for me. All right. So actually, you should probably try starting out this one. Simple pendulum has a mass of 0.25 kilograms, length of 1 meter, displaced through an angle of 15 degrees and then released. And we want to figure out max speed, maximum angular acceleration, maximum restoring force, and maximum linear acceleration. So I'll give you a few minutes to try to set this up. You can ask questions on the side, and I'll answer them as you ask them. We are going to use energy, yes, for maximum speed. So you do know the maximum angle, so we can talk about potential energy and kinetic energy. What's going to be the hard thing to get for the energy, though? Yeah, we're going to use the angle to find the height. It's going to be similar to the picture I drew out in the previous question, though. We can't just immediately use an angle theta. It's going to be a little bit messier than just directly using the angle for height. So I know a few of those, but just like before, we only care about our height from the lowest point here. We know this entire length is 1 meter long. We can force this to be a right angle right here. So think about what side you need to solve for on that right triangle, opposite or adjacent. Force? What about force? Oh, forced it to be 90 degrees. Yeah, I mean, honestly, that's what a lot of math and physics is about, is trying to force things to be 90 degrees. In reality, I think in pre-cal they made you derive the law of sines and cosines, and you did that by forcing things to be 90 degrees. I mean, you'll get to linear algebra. It's called linearly independent values, but yeah, you want everything to be either perpendicular to each other or zero. It's one of the most common things in all of math. All right, so 1 minus cosine 15. So why'd you get cosine? So cosine is opposite or adjacent. All right, so yeah, we're trying to find the adjacent side of this right triangle, and you use cosine, that's correct. So cosine of 15 degrees is going to be the adjacent divided by the hypotenuse. So cosine of 15 degrees, my adjacent is what I'm looking for. My hypotenuse is at 1 meter. So adjacent is going to be 1 meter times cosine 15 degrees, which is what you got here. You have 1 cosine 15 degrees here. So this is just from here to here, this length here. This whole length is 1 meter, so I could do this minus this to get this. So my height is going to be that entire 1 meter right here, minus that 1 meter times cosine 15 degrees here. And I actually don't have that solved, what that comes out to. Wait, 0.0341 meters. Yeah, and I'm going to keep a few more digits because this is an intermediate step. And again, this is a thing we've done a lot of times. Again, the length minus length cosine theta, right? A lot of times we've seen this before, where height is length minus length cosine of the angle. Honestly, out of all the trig, I expect them to ask this right here is one of the more difficult trig questions. They're not really trying to destroy you with trigonometry, but I would 100% definitely be able to do this just in case that does show up where they expect you to do that. Now, even if you can't figure all this out, we can still get some points here. We're trying to find the maximum speed. Like a lot of you have already said, we're looking at energy. So I know total mechanical energy is going to be conserved. It said nothing about losing energy along the way. Total mechanical energy initial equals total mechanical energy final. So I'm going to call this point here initial, this point here final. So what type of energy do I start with? So we start with gravitational potential energy, and then we end with kinetic energy. And again, released from rest, so no kinetic energy there. All right, so we start with gravitational potential energy turning to kinetic energy. So mass times acceleration of gravity times initial height is equal to 1/2 mass times final speed squared. Again, mass divides out. Mass isn't going to have an effect on the speed. I can multiply 2 over 2 times acceleration of gravity times initial height is final speed squared. So my final speed, the speed at the lowest point, is the maximum speed, right? Lowest potential energy, most kinetic energy. Square root of 2 times 9.8 times 0.0341 meters. Yeah, it rounds to 0.818 meters per second. And you actually really could have used kinematics for that one. It would have been the same as if you just dropped something from this height. All right, everyone good on that one? And again, even if you have a mental block and you really can't remember how to set up your trigonometry, if you at least go here and set up your energy equation, that's going to be worth some points. So I could easily see a question like this being a 3-point question, 3 or 4 points, and you can easily get 2 or 3 of those points without even getting the trig right. All right. B wants us to get our maximum angular acceleration. Where should we start on this? All right, so max torque at the highest point. Yeah, you could use torque. I'm not going to use torque, but yeah, the torque would work just fine. Actually, yeah, why not? Yeah, I was looking at force, but yeah, no, torque will work just fine. So at the highest point, we're right here. We should probably draw a free body diagram. So obviously, I have gravity down. Tension is going to be up and right. Is tension bigger or smaller than the force of gravity? Yeah, so at the highest point, we're going to have a smaller tension than gravity. Again, the string isn't holding up the entire weight. The string is only holding up a little bit of the weight, and then some of the weight is going over to pulling it down and away. Torque you could use. I mean, you can abuse kinematics a lot, but not always. So we're going to have to split one of these up. Well, it's going to swing down this way, so I'm going to split up my force of gravity because I want everything along the string or perpendicular to the string. So either perpendicular to the direction of motion or parallel with the direction of motion. So if I draw this out, larger. I know this angle right here is 15 degrees. I'm going to have some amount this way, which is going to cancel out with my tension. Some amount this way. This is the one I actually care about. This is going to be my parallel component of force, my perpendicular component of force, my tension. So I know this angle is 15 degrees. This line is straight down. This line is straight down. So this angle right here is 15 degrees. I'm trying to find the angular acceleration, that sideways acceleration, not the centripetal acceleration, which is towards the center of the circle. So which side am I looking at? The perpendicular or the parallel side? Yeah, we're looking at the parallel side, so we're looking at the opposite side. So our opposite sign is going to be sine. So sine 15 degrees is going to be opposite over the hypotenuse. Our opposite side is what we're looking for here. Divided by the hypotenuse force is going to be the weight, which we didn't actually solve for that yet, but the weight is going to be 0.25 times 9.8. A quarter of 9.8, what was that, 2.45 newtons, I think. 0.8 divided by 4, yeah, 2.45. So our parallel component of force is going to be 2.45 times sine 19. Not sine 19, sine 15 degrees. So we get 0.634 newtons. And look at that, we solved number C, letter C. Isn't that convenient? Right, maximum restoring force. So restoring force is the force pulling me back down towards equilibrium. So the further I'm pulled up, the more my restoring force is. So if I found my force at the greatest angle, that's also my maximum restoring force. So we already solved C, and we can work backwards to get B. So we're trying to find that acceleration. So that parallel component of force is going to be mass times that parallel component of acceleration. So 0.634 newtons is equal to 0.25 kilograms. 0.25 kilograms. That's times the parallel component of acceleration. 0.634 times 4. I can't do that in my head. 2.536 meters per second squared. But is that my angular acceleration? Oh, well. Yeah, this one is nice. But yeah, so it will end up being the same. But yeah, that's my tangential acceleration. I'm still going to solve it out, even though you're right. So my tangential acceleration is equal to the angular acceleration times the radius, right? Remember all those. The angular quantity times the radius gives you your tangential linear value. But yeah, you're right, because this is just 2.536 equals angular acceleration times 1. So yeah, our angular acceleration is just 2.54 radians per second squared. And then, Tan, did you use torque? If you're still here, I don't know if you left. But yeah, if you used torque, you should have still gotten the same answer. What was 3A? The maximum speed was 0.818 meters per second. All right, D wants to know the maximum linear acceleration. Now, this is kind of iffy. I don't actually know what the person who made this was asking for, and I don't have my answer key here. So let's look at this two ways. Well, I know my maximum tangential acceleration. So tangential acceleration max. Well, we already figured that out. That was at 2.54 meters per second squared. What other way could we accelerate, though? Total acceleration? We could look at total acceleration. Yeah, that probably is actually what they're asking about. So yeah, what else do we need to get total acceleration? Kinematics. Kinematics won't. Actually, it would, but you would need more information to use kinematics there. So we can also look at our centripetal acceleration. And where are we going to have a big centripetal acceleration? Yeah, the highest speed, which is the lowest point in the motion. So maximum centripetal acceleration, let's draw our free body diagram. We're going to have a really large tension up and a small weight down because we have to move down and then back up. So I need that bigger upward force in order to turn me. So the pendulum is going down. I need a bigger upward tension in order for the pendulum to start moving up. And then centripetal force is that net turning force. So centripetal force is going to be the tension minus the weight. Yeah. So yeah, we're going to have to solve for a tension here so I can add weight over. So centripetal force. Actually, we're doing a little bit extra here. That's what's happening. Just because I might ask you to solve for tension later. So tension isn't actually needed to solve this question. I'm just doing some extra information that would be really good to know for the test. All right, so centripetal force, mass times centripetal acceleration, plus mass times acceleration due to gravity is equal to tension. Or mass times speed squared over radius plus mass times acceleration due to gravity equals tension. So we have a 0.25 kilogram mass moving at the lowest point, 0.818 meters per second, all squared, divided by a 1 meter radius plus 0.25 times 9.8. So tension, again, not needed, but something you do need to be able to do for the test. 0.25 times 0.818 squared plus. So if we do this, the tension at the lowest point is going to be 2.62 newtons. All right, so make sure you can do that for the test. But we didn't have to go through all of that. I could have just solved for centripetal acceleration using centripetal acceleration as speed squared over radius, or that 0.818 meters per second squared divided by 1 meter. Should equal right around 0.67 meters per second squared. So which acceleration is having a bigger effect? The tangential acceleration at the endpoints or the centripetal acceleration at the lowest point? Yeah, so this acceleration at the endpoint is going to have a bigger effect. So maximum linear acceleration is going to happen at the maximum displacement. So it'll happen at your angle is equal to plus minus 15 degrees. One way of writing that. So yeah, so we're going to have the biggest linear acceleration at the endpoints because at the lowest point, I do have centripetal acceleration. You could argue that's not a linear acceleration. I don't know. It's kind of a weird way of asking it. I wouldn't state that as linear acceleration. I would state it as tangential acceleration or centripetal acceleration, but whatever. Any questions on those? I know we've been kind of going for about 2 hours. So sorry it went a little bit longer than expected. Any last minute questions about the lab? Is everyone just writing right now? Oh, is my chat not keeping up? There we go. It wasn't keeping up. Position A, the lowest point P is. Wait, is this a question on the review on College Board? For the pendulum one, initial position A, lowest position B, 30 degrees from the horizontal, which are the two arcs? AP, wait. Where's B at again? From the horizontal P. Yeah, are you that question? Is that a review question, or is that just a different one? Because I'm not. That's like I'm not visualizing it very well in my mind. Yeah, ask a lab question. Yeah, so the rubber band, I was not expecting the graph to be linear. Yeah, so that's kind of to be expected. So try to find a range where it is linear. It's the rubber band probably started off looking relatively linear before it probably ran away looking more like a quadratic. So yeah, I'm expecting your graphs not to look the best on the lab. I care more about you getting the correct type of graph than the graph looking perfect. What's your lab question, Tam? Oh, there it is. Why is my thing not scrolling down anymore? For part 2, I mean, something went wrong. I saw yours. You had a acceleration due to gravity of 12.5. You should not be getting that big of a percent error for that. You should be getting about a 25% error. So I don't know what's happening there. Do we? You don't need to. You can, if you want, print out everything and take a picture of it. But you can just the lab evaluation. You can just write it on paper. So I guess the minimum just right there. You can just write it out. There's not a whole lot to that. You're talking about the group evaluation part? Yeah, you're going to take a picture of that and submit it. So you could fill it out either in a Word document. You could print it out and fill it out, or you could just write it on a piece of paper and fill it out. Well, this video's kind of gone on long enough. I'm gonna stop recording here. So, but I'll keep answering questions for just a little bit.